I guess we'll get started. It's 1:30. I'm Doug Creighton. I'm the data science lead at Statflo. We'll go into what Statflo is in a bit, but I run most of the data innovation projects, data analytics projects, and integration projects at Statflo. And then is the founder of Arima. It's a synthetic data company that's created, database of individual consumer level behavioral and demographic attributes across the Canadian population. This database really allows, data scientists like myself to build more robust ML models by connecting their existing data sets with synthetic, individual level consumer intelligence. And this is without raising, privacy red flags as it's synthetic. Arima is going to be the full staff solution for data scientists to build the most complete data set of the consumers to power, the best results for their ML models. Prior to founding Arima, Winston was the director of data science at PwC and Omnicom Mediacom. Which I'm sure many of you have heard of both. Winston is also a part-time faculty member at Northeastern, University of Toronto, and also sits on the advisory board of the Master of Analytics program there. And so how do you click what slide are we on right now? I can't see.
Okay, well, let me maybe take it over from here.
Yeah.
And I can start the presentation.
Perfect.
All right. Hello, everyone. Thanks, Doc, for the introduction. The title of the talk today is a machine learning-based privacy-preserving framework for generating synthetic data from aggregated sources. This presentation is jointly done by myself and Doug, and we'll talk about the theoretical foundation of how synthetic data generation works in our specific case, generating synthetic population data, as well as a few business applications of how that helps companies to derive value. All right, let's get started. So the first thing we want to discuss is what exactly is a synthetic population. It's a term that might be foreign to a lot of statisticians or data scientists, but it's quite a common technology that people in the social sciences or people in the consumer analytics space use. So here, as it says, a synthetic population is a statistical reconstruction of individual level data where the ground truth is not available. In many cases, when we're dealing with people-level analytics projects, like analyzing churn, analyzing what people do, people's behaviors, for example, we'd like data on these individuals. But very often, you can't get that data very easily. The ground truth is not available. And it's typically not available either because of cost of data acquisition or privacy, or in many cases, both. So instead, what we have are aggregated data sources. And what I mean by aggregate is usually they're averaged or they're summed up to a certain unit, and the aggregated data is released instead of the individual form. In Canada, data is usually aggregated to postal code level, so just by aggregation by geography. And what we want to do is we want to take the aggregated data and try to produce a synthetic version of the underlying data that was aggregated to produce the aggregated sources. And that process is called generating a synthetic population data. From a data science perspective, a synthetic population is statistically equivalent to the real population, meaning that if you were to train models or if you were to build predictive analytics on top of a synthetic population, it should be the equivalent to training data from using the real population data, even though the two are not necessarily the same. So they don't necessarily match one-to-one. They're rather statistically equivalent. So why is this work important? Well, as a data scientist, some of the challenges we face when we work with multiple data sources are fragmentation, meaning that we deal with a lot of sources and they all sort of have their own data structure, their own metadata formats, and it's not very easy to combine these data sources together. Privacy being the other reason, as we've discussed, because of privacy concerns, we often have to work with aggregated or anonymized sources. And the challenge of these, these two challenges lead to the third one, which is there's no obvious ways to link data sets together. When you have, let's say, 5 different data sets, your first party internal CRM data, maybe the census, maybe some third party data that you bought from some vendors. They don't have, they don't have they sometimes don't have names or addresses, user IDs, things like that, where you can join these data sets together. So trying to harmonize the data is very difficult. So the key question we want to answer here is how can we create a data fusion from all of these sources to produce a more consistent, accurate, and useful data set for modeling. And as I've discussed, most of the applications that we want to address with this data set is either geospatial, in other words, understanding the geography of a certain area. So things like site selection or traffic prediction would fall into this segment, or customer level, consumer level analytics, things like predicting behaviors, lookalike modeling, churn analysis, and so on. So we'll get into the science of what a synthetic population is, and how do we actually generate one. I'll start with an example of what's the goal. What's the goal of generating a synthetic data? Typically, this is what data. This is what's data. The commercially available data looks like, where you have different postal codes. Let's say take the first postal code A1A1A1. You know how many people live in that postal code, and you know the distribution of attributes of people in that postal code. So for example, 53% of the 53 people are between 20 to 29. 12.5% of them are between 30 to 39, and etc. You also know 71% of them have dogs, 36% have own SUVs, and 67% watch TSN. And you have, at a postal code level, what the attributes are, the distributions of the attributes, so to say. The attributes can be either binary, either yes or no, in the cases of, for example, owning a dog or have an SUV, or they could also be multi-categorical. So things like age, for example, would follow one of those. It would be you would have multiple classes. What we want, what's more useful, is not to work with the postal code level data, but instead to have the individual level data, so the data frame below, where for a postal code like A1A1A1, you actually have 53 distinct records, because there are 53 of them. So you want to see things like the first person, well, they're 39, they're 30 to 39, they have a dog, they don't have an SUV, they watch the TSN. And the second person might be 40 to 49, they don't have a dog, but they have an SUV, and they also don't watch TSN, and so on. The reason why the second view is more useful than the first one, as you can imagine, is it gives you more granularity. It tells you how people are different in that postal code, and it tells you how attributes correlate. So when you have one specific customer, let's say from that postal code, it's very easy to work with the individual level data, but it's difficult to work with averages. So the point of the synthetic population is to take data sets that look like the top table and try to generate data sets that look like the bottom table. So how do we exactly do that? Well, the methodology that I'll present today is called the sync framework. It is an algorithm that we've developed and published, which takes aggregated level data and generates the more granular individual level information. The paper is published, as I said, the reference is below, which if you're interested, you can take a look, and also brings tangible business results, which are things that Doug will present. In this framework, the key assumptions we're making are: one, correlation is preserved under aggregation, meaning that we assume that if variables correlate at a postal code level, then it also correlates at an individual level. The second assumption we're making is that individual level synthetic data needs to be calibrated to match the given aggregated data. And what that means is going back to the slide here, if you take the lower data frame, if you take the data set below, and if you aggregate it up by postal code, then you would get the top data frame. So in other words, our data is consistent at the postal code level given the original data source. All right, so let's take an example. I'll use a very, very simple example just to show how sync works. We're not going to get into too much technical detail here. For those who are interested, you're of course more than welcome to discuss with us afterwards or to look at the paper. But let's say we've got a postal code where we've got 3 people, just 3 people, their age distribution, their profession distribution, education, and marital status. And what we want to do is we want to fill out the table below. That's the individual level table. So we've got 3 unique IDs, 1, 2, and 3, and we know their age. We'll just, for the sake of argument, call the youngest person 1, name the 35-year-old person number 2, and the 60-year-old person number 3. And our goal is to fill out their profession, their education, and their marital status in such a way that makes sense, make intuitive sense, and also that would respect the postal code level constraints. And we do so sequentially by looking at conditional probabilities. So in other words, we look at the probability of profession given age, and then education given profession and age, and finally marital status given education, profession, and age. So we do that one variable after the other. And we do so by first finding a suitable approximation of conditional probability, which we take the model and train it on the postal code level data. And we assign values to individuals based on relative likelihood. So what does that mean? Let's suppose that we made the following predictions based on our approximator, whatever approximator we choose. And we've calculated that for the first person, the probability of them being a construction worker, given their age, is, let's say, 40%. The probability of them being a IT consultant, given the age, is 35. And the probability of them being a healthcare professional, given the age, is 25, let's say. We do that for everyone. And now we look at the relative probabilities. So for the first person, we see that he or she is most likely to be a construction worker, given the matrix we've calculated. So we'll assign that value. And now once the slot has been filled, remember that we've only got 1 construction worker in this neighborhood. For the second person, despite the fact that there's only he or she is equally likely to be a construction worker versus an IT professional. Because the construction worker is taken, we're only left with IT, so we'll fill that in. And for the last person, what's only left is the healthcare, so we'll fill him in for that. And we've done, so now we've completed the first column of the data frame. One thing I should note here is that we're discussing, we're talking about relative likelihood here. So in other words, we're not saying someone who's 25-year-old will be an IT construction worker. We're just saying that he's more likely to be a construction worker than the other 2 people living in that postal code. And similarly, we do it for the rest of the with the rest of the variables sequentially. A couple of things to consider. First of all, in this methodology, order matters. So in other words, how you assign the order is important. And this is why you want to start with your most generic variable first, followed by your least generic variables. And to avoid conditioning on too many variables, we typically pick a core feature set, and you only condition them on a feature set. So in our case, when we generated our synthetic population, we took about 20 variables, and they're all sort of demographics variables like age, income, education, and such. And we believe that that core set of features is enough to predict conditional probabilities. So we're not consistently adding into that feature list. That feature set stays the same throughout all of our variables. And the advantage for that is that you don't have to retrain every time. So when you update one variable, you don't have to train all of the conditionals before that. You just have to, you just have to update one variable at a time because they only depend on the core feature set and they don't depend on one another. So I wanted to talk a little bit about the synthetic population data set we've built and what that looks like. So Arima, as we said, we have developed a synthetic population, which we use that to help data scientists to develop better and more robust models. Our synthetic population data set is built from 21 different sources that ranges from open data, things like census or market research, census or StatsCan, to syndicated research, so data that we buy from other market research companies, to data partners, which includes things like credit card tracking, credit ratings, location tracking, and more. And of course, we're always looking for new data vendors to join us and work with us on a rev share basis to bring their data into the synthetic population. Our synthetic population is national, based on all 37 million Canadians with 4,000 plus variables. And of course, because the data is model generated, there's no PII, so it's completely safe to use. And what we do is we take away the tedious work around data acquisition and data cleaning so that our customers, data scientists, can focus on building models with our data. How does our synthetic population work? And I think this is a very important question. If you'd like to develop your own synthetic populations as well. Here I've sort of given a flow chart of how the system works. So let's assume that our friend John here is a data scientist. He's looking to build models to better understand his customers. And some of the challenges he faced are, his internal first-party data could be very messy. He only knows how his customers interact with his own brand, and he doesn't have the time or effort to deal with, many different vendors and acquire third-party data to enrich his own data sources. So what we help them do is we apply a process called the probabilistic matching, where John tells us what he's looking for. So, and instead of sending out names or email or addresses, which would be a deterministic match, he's sending us things like age, gender, and postal code. And we take that information, we match it to individuals from our synthetic population, and we return him the variables that he's looking for. So as an example, he's got, let's say, a customer, 25-year-old male living in this postal code. And he asks us, we want to know whether that person uses Facebook, whether they're planning to buy a TV, whether they have a car, and so on. And through that API call, we send the correct data back to him, so he can use this data to enrich his first party data and build better models. Very simple. You send data in, and you get whatever you want back. So now I will hand it over to Doug, and he'll present a case study of our work, which we did using our data plus their internal first-party data, and how we're able to build better models. So over to you, Doug.
Great. Hello, everyone, again. So before getting into the case study, it's really important to understand what is Statflo and what do we. So Statflo is a one-to-one business text messaging platform that works seamlessly with your existing systems. We have customers from mid-level retail to enterprise across North America, including some of the biggest companies in Canada using Statflo today. The goal of Statflo is really to connect your consumers with in a personal way to increase your customer experience and increase your gross profit through additional sales by staying top of mind. Right time, right message, right opportunity. You go to the next slide. So before getting into the case study, one too far. Back one up one. Yeah. Before getting to the case study, I just thought it would be really important to explain the different type of campaign models that we have at Statflo. And this might be nomenclature that I just use at Statflo, so I'm going to be using it in the case study. So we have a sales cycle model and then a general retail model. And a lot of our clients, or most of our clients, are in the telecom space. So when we're talking about the sales cycle model, we have a conversion event that ends that sales cycle. So if you and then you were to renew the phone, that would be that conversion event. And basically, we have optimized our campaigns within the sales cycle to hit them at the right time and have the right opportunity to to make sure that conversion rate is the highest it can be. So we don't want to change any of those campaign time periods. They are where they should be. And then we have the general retail model, which you basically would have different opportunities at the right time based on the customer, and you have campaigns on different products or at different times depending on their previous purchase history. And that's not what the case study is up today, but it's also a way we can use this data. And so to get into the case study, I'll go to the next slide. Basically, what we want to do in this sales cycle model is to add any additional opportunity to each campaign. So what this will do is increase the bag size and total sales cycle GP if we can get it on every single outreach. And then we want to be able to nudge the consumer to other products at every outreach. Because again, we don't want to move the campaigns. They're where they should be, but we want to add the ability to do that with new products if those products are the right time to sell them. And again, this is all about keeping top of mind and keeping in front of the customer of the products you sell to have that one-to-one approach. So when they think of technology in the telecom space for our telecom clients, they're thinking of you. So they're thinking of you for TVs, watches, tablets, whatever you happen to sell at your store. And you're their guy for that. And so that is what we're trying to do. And what we wanted to do with Arima is increase the amount of the probability that we'll be hitting the right moments for those customers in those existing campaigns that we're running. So next slide. So very simply, this slide's is that here are our results on our sales cycle. So in our existing renewal campaigns, or those sales cycle campaigns, we wanted to cross-sell wearables, which included watches and activity trackers and other health products, and then cross-sell that. And then we also wanted to cross-sell tablets as well without distracting from that renewal purchase. And so we used our existing data, transactional data that we had combined with conversational data, and then we added that with Arima's features with the joins that we can to create that synthetic features for our ML algorithm. And you can see in the results there was really big improvements on precision for both algorithms, for both products, I mean, and then decent amount of improvement on recall. And for those that aren't ML minded, what this really means is that we are, for precision improvement, we're not cross-selling customers that shouldn't be cross-sold. So that saves our customers time, and it also Winston, are you sharing the screen? I don't see it anymore. Anyways, I hope everyone else can see the screen. I can't see it anymore. So precision's gone up in some cases from 6% to 74%. And what this does is that we're not, cross-selling customers that don't need to be cross-sold. Oh, it looks like other people can't see the screen share anymore. Maybe something went wrong, but I'll try to go over the bits and describe the slide. There's not too much there. And then the recall improvement, what really happens here, and this is, I think, the most important for this use case, is we're adding more high probability clients into our cross-sell. So we're not missing anyone. We're already contacting them anyways. So adding that additional nudge, though, does take time. It's monumental to the amount of starting a conversation. So for me, the recall improvement specifically on tablets was a huge benefit to Statflo, because it was classifying more people as, hey, this person would probably want to buy a tablet now. Now, we've just started this experiment this month, so I do not have conversion results, and that's obviously the most important thing to any experiment. I will have them, early 2021. And if you want to hear how the updates are, you can feel free to add me on LinkedIn and such. But we really wanted to focus here on the model improvements. As you can see, those features and those synthetic features really did have a benefit. And it's mostly because likely that those features that we're adding in from Arima really just help describe that person better. So not just, did they buy a tablet before? It's more, would this person buy a tablet, or would they buy many tablets? Because as you know, like somebody who's a is part of a family, is in a neighborhood that has lots of families, are more likely to buy more tablets for each of the children, specifically for education and other purposes. So those type of features really do help predict someone's buying behavior more than just, your simple transactional data. And I'll hand it back to Winston. I think you're back on right now, Winston, or no? I think there's some technical difficulties because I don't see him. Sorry about that. I don't know what, maybe his computer froze. I don't know. I could try to answer some of these questions in the meantime. Oh, here it comes. Great. Perfect. So I think we're at the last slide, Winston. I just finished.
Hello, everyone.
Notes. And so success stories and then Q&A.
I think there's a bit of a technical issue. So maybe I can quickly address some of the questions that's being asked.
Yep.
One question here says, has synthetic data been compared to real data in terms of ML implementation? And the answer to that is yes. We've seen that in the example that we've presented, where we used synthetic data to improve model accuracy. And also in the paper that I published, we did a study where we took synthetic data and we compared that. We again tested for model improvement against various data sets. Another question. What are some metrics you use to calculate the accuracy success using synthetic data? We do that in two ways. The first way we do is by looking at how well the reconstruction is. So we took a data set, we aggregate it, and then we use the sync framework to bring it back, and we compare the accuracy of the two data sets, the data with the original, and also, of course, through applications like the ones you've seen, where we've used it to demonstrate that it does improve model accuracy. What else is there? How do you determine that individual synthetic records are better for training models than aggregated records? Isn't it information contained in both the same? Well, I don't think it is the same, because if you're using aggregated data, then you're aggregating against the postal code. So one of the assumptions you're essentially assuming is that everyone in the postal code is the same, right? So let's say if you have 5 customers, they're all living in the same building. If you were to use postal code level data, then they would basically all look the same. You might append over the average income, let's say, for all of them. But when you're using an individual level source, of course, then they can be very different. So I think you are getting extra information out of that. Questions here. I'll share the link to the paper, so that has been done. Thank you. What are the limitations of synthetic data? For example, is there a way to create a synthetic data on historical transactions which is able to replicate the performance and preserve the relationship between historical patterns? This is actually something we've tried, where we took lists of historical transaction data and we try to generate new data based on the history. I think there are always limitations, and synthetic data generation, you need to have additional information, not just the data itself, but also additional information. So in our experiment working with generating transaction data, we're also taking things like macroeconomic factors, things like the GDP and so on, to improve the quality of the synthetic data. Did you happen to consider using autoencoders to generate synthetic data? I did. That unfortunately didn't work very well. This is not a true synthetic data generation problem, in the sense that we're generating data. We're only generating similar records, there's also a component of downscaling. So you're also taking aggregated data and generating individual level data from that. So that's why autoencoder in our case didn't work very well.
There's a lot of questions from when you were talking, Winston. Do you want me to name them out? I have them listed if you're still searching for them. So one question right at the beginning was, I guess a potential flaw of the method is that, Winston, are you here still? Oh, you're back. I'll wait till you come back. I was just getting questions right from the start of the talk, if you don't mind. So someone wrote, I guess a potential flaw of the method is that it could have the inaccurate data set. For example, SUV owner typically goes to older people who are richer, but TSN watcher is typically with younger people. How do you mitigate this issue?
Yeah, so that depends on the quality of the source, definitely. I mean, if the source is accurate, then the quality of your data set should be better. So the way when we generate our synthetic population data, we took sources that are compiled from, let's say, through different means. So we're not just using internet data, we're not just using data from one source, but we're trying to balance between, for example, traditional paper-based surveys, they tend to appeal more to the older people, whereas internet-based data tend to appeal more to younger people. So we try to find a balance between the sources.
Okay, and then the next person wrote, how is it possible to construct individual data when you have only aggregated data? I think you've addressed that in the conversation, but in the presentation, but it was the question anyways. So the next one is in calculating marital status, did you consider occupation and the other attribute?
In the calculus, did you consider occupation? And yes, so when you calculate the marital status, it depends on everything before. So it happens in a sequential way.
I think you addressed this already too, but what are some metrics you use to calculate the accuracy or success in using synthetic data?
Yep, that has been discussed in the paper where we looked at taking a data set, aggregating it, and then using sync to bring it down to an individual level again. So that way we compared the two data sets and we found which one was more effective. And we also do that through running a number of models. So we want to say, here's a model. Here's the model with synthetic population data added into it. Does it actually bring better results?
Okay, the next one was, how do you ensure there is no built-in bias in constructing the individual level data, though it is consistent with the aggregated data?
So that comes again down to the source, especially coming down to your core feature set. You want your core feature set to be as unbiased as possible, otherwise the whole system could be biased. So your core feature set in our case is a census, and that's simply the most unbiased source that we can find because everyone in the country has to respond to the census.
Mm-hmm. So how do you determine that individual synthetic records are better for training models than aggregated records? Isn't the information contained in both the same?
No, I don't think so, because when you're talking about, let me give you an example. Let's say you've got 5 customers living in the same building. Then if you're using aggregated data sources, then they all look the same. You have no better choice than to use, let's say, the average income for that postal code as a proxy for the 5 customers. But when you have a synthetic population, because it's factoring, as you're building the synthetic population, because it's factoring things like age, gender, family, and all of the other factors, your individuals are different. So it's almost like calculating conditional probabilities, where in one case you're only conditioning on the postal code, and in the other case you're conditioning on postal code and other factors. So it's a better, let's say you're getting a better approximation because you're conditioning on more variables.
Mark asked, can this solution be fully integrated with Google Data Studio for online digital sales and marketing campaigns?
Yes, we have APIs available for you to do that.
Sean asks, does sync generate outliers?
It tend not to, but you can specify the distribution of the variable you're looking for so that it generates outliers.
I might have answered this one, but Julie asked, what are the limitations of synthetic data? For example, is there a way to create synthetic data on historical transaction data which is able to replicate the performance and preserve relationship between historical patterns, etc.?
Yeah, that's a good question. Well, like every method, there will be limitations. So in our case, we are looking at in our case, we try to add in other factors. So we're not just generating synthetic data based on the data itself, but we're also trying to add in things like, GDP, the macroeconomic conditions, or things like that, to make sure that the synthetic data we generate preserves, sort of is more relevant to the current market conditions, so to say.
Cyril asked, and Michelle asked as well, can you comment on where to get the conditional probabilities from when generating artificial examples?
Yes, you train that on the postal code level data. So that's the assumption we're making, where correlation is preserved at the postal code level. So in other words, if at the postal code level two things are correlating, then we also assume that at an individual level the two variables correlate as well, and hence we can use the conditional probabilities trained on the postal code level.
I think that was all the questions. We kind of scattered through those, but I try to get through all of them. So if I missed yours, if you can comment again, and we can quickly answer them, or if there's any other questions that anyone else has. I don't see any. So if you would like to connect with either of us, here's another one. How do you decide what are the features and columns you add to generate the synthetic data?
Oh, that's up to you. Well, whatever you feel is useful, then you add that in. So the way we generate synthetic data is purely based on our business needs.
Yeah. So I think you have 4,000 columns, correct me if I'm wrong, and you can join on the features that are most relevant to you, and then add in the features in order that you would want to train your ML algorithm.
Yeah.
So it's completely up to you as a consumer. There's 4,000, but you might only need 5. You may need 70. It really comes out to your business objective. Yeah. Is that right?
That's right. Yeah, exactly.
Yeah. Great. Yep, I'll write my stuff. I don't see any other questions, but if you have any, just let me know. We'll be here for an extra 30 seconds, 40 seconds, but I think we answered all of them. Thanks everyone for joining. This was great. We had a lot of interesting, really great questions. I think even using the stuff, I learned a lot from those answers. So thank you for asking them. Winston put his information in here, and I put mine there as well. But you can connect with us after if you're interested more in what Arima is offering and how it could help your ML models get better. And you can experiment with it and see, like you can see the same results that I shown. You can easily experiment and see very quickly, adding those other features, rewriting the algorithm to see if it's beneficial to you. And if you want to catch up on the results that I have on conversion rate, connect with me and we can keep in touch that way as well. But thanks everyone. And Winston, you have anything else to say?
I'm good. That's all I need to say. Thank you.
Okay, great. Well, thanks everyone, and we'll connect with you in probably different talks and networking as well.
Thank you.